Hello guys, today we have something very interesting. I'm going to be proving that the absolute value of x minus 2 plus x is greater than 0 for all real values of x. And I'm going to be doing so in three methods. In the first method, I will simply show that this expression, the expression on the left, is always positive for any real value of x. And in the second method, I will solve this inequation normally and show that the solution set is just the set of real numbers. And thirdly, I will show this by using the graphical method. Okay, I'll start with the first method. And I'll start by defining the absolute value of x minus 2. And we know the absolute value of x minus 2 is just x minus 2 if x is greater than or equal to 2, or negative into x minus 2 if x is strictly less than 2. And notice that they said x such that x is less than 2 union, they said x such that x is greater than or equal to 2, that's the complement of the first set, is equal to the set of real numbers. And so, to show that the absolute value of x minus 2 plus x is always positive, I need to show that it is always positive for this first set and for this second set. And so if I show that that expression is always positive for all values of x less than 2 and for all values of x greater than or equal to 2, then I've proven that the expression is always positive for all real values of x. Okay, now we start with the first set. We know that if x is less than 2, then the absolute value of x minus 2 will be equal to negative into x minus 2. And therefore, the expression, the absolute value of x minus 2 plus x will be given by negative into x minus 2 plus x, which is equal to, if you open these brackets, we're going to obtain negative x plus 2 plus x. And if you simplify this, we're going to have 2. Remember, negative x plus x is 0. And we know that 2 is greater than 0. Good. So what are we saying here? That whenever we pick a value which is strictly less than 2 and substitute in this expression here, the result will always be 2. And we know that 2 is positive. Let's take, for example, let's pick 0. We know 0 is less than 2. If you substitute 0 in this expression, we're going to obtain here we have 0 minus 2, which is negative 2, and the absolute value of negative 2 is 2. 2 plus 0 is 2. If you pick another number, say negative 10, remember negative 10 is still less than 2. If you substitute negative 10 here, we're going to obtain negative 10 minus 2, which is negative 12. And the absolute value of negative 12 is 12. And 12 plus negative 10 is just the same as 12 minus 10. And 12 minus 10 is 2. So, whenever we pick a value which is less than 2, this expression will always give us 2. And we know that 2 is positive. So, we take the second branch. The second set says that if x is greater than or equal to 2, then the absolute value of x minus 2 will just be equal to x minus 2. And therefore, the expression x minus 2 plus x will just be the same as x minus 2 plus x, which is equal to 2x minus 2. And if you factor out 2, we're going to obtain 2 into x minus 1. Good. So if x is greater than or equal to 2, then x minus 1 will always be positive. Pick any value from 2 upwards and substitute here. This result will always be positive. So this expression is always positive for all values of x that are greater than or equal to 2. Therefore, we are saying that the expression this is always greater than 0 for all values of x that are less than 2 and for all values of x that are greater than or equal to 2. Therefore, we're going to conclude that the expression x minus 2 plus x is always greater than 0 for all real values of x. For all real values of x. That is what we are supposed to prove. So this is the end of the first proof. We take the second method. And in the second method, like I said above, we are going to solve the inequation, the absolute value of x minus 2 plus x greater than 0 normally, and then we show that the solution set is just the set of real numbers. And to solve this inequation, I will also start by defining the absolute value of x minus 2, like we did in the other method. So we know that the absolute value of x minus 2 is x minus 2 if x is greater than or equal to 2, or negative into x minus 2 if x is less than 2. And notice also that they said x such that x is less than 2 union, they said x such that x is greater than or equal to 2 is the same as the set of real numbers. So we're going to find that subset of, let's call this A, and we call this B. So we're going to find that subset of A that satisfies the above inequation, and also we are going to find the subset of B that satisfies the above inequation. Let's call that subset of A, A prime, and that of B, B prime. So at the end, we're going to find A prime union B prime in order to have our solution set. So to find A prime, we start with the set A. So if x is less than 2, then the absolute value of x minus 2 will just be equal to negative into x minus 2. And therefore, the above inequation reduces to negative into x minus 2 plus x, which is greater than 0. And this implies that negative x plus 2 plus x is greater than 0. And we know negative x plus x is just 0. And we're left with 2, which is greater than 0. Now we know 2 is greater than 0. This is always true. And therefore, all elements of this set will satisfy the above inequation. That is, we are saying that A prime is the set A, which is just the set x such that x is less than 2. We look for B prime, and to look for B prime, we start with the set B, and we know that if x is greater than or equal to 2, then the absolute value of x minus 2 will just be equal to x minus 2. And therefore, the above inequation reduces to x minus 2 plus x, which is greater than 0, and this implies that 2x minus 2 is greater than 0. And if you add 2 to both sides, we're going to obtain 2x greater than 2. And if you divide both sides by 2, we're going to have x, which is greater than 1. So at this level, we're going to find the intersection of this set and this other one. And we're going to do so by using a number line. So here we have 1, and here we have 2. So let's start by representing this set on the number line. So we start from 2, including 2. So we use a closed circle at that level. And we draw an arrow pointing to the right. In the second set, we have x, which is strictly less than 1. So we also draw an arrow there pointing to the right. So clearly we can see the intersection. The intersection starts from 2 upwards. Therefore, the set B prime is the set x such that x is greater than or equal to 2. Therefore, our solution set is the set A prime union B prime, which is the set x such that x is less than 2 union the set x such that x is greater than or equal to 2. And this is just the set of real numbers. Therefore, the solution to this inequation is a set of real numbers. That is the second method. So we have proven that this inequation is satisfied by all real numbers. That is exactly what we were supposed to do. Okay, so this is the end of the proof for method 2. So the third method, we're going to use a graph. And we know that if the absolute value of x minus 2 plus x is greater than 0, then we can still represent the inequation like this. It can still be written this in this form. So just by subtracting x from both sides, we're going to have the absolute value of x minus 2, which is greater than negative x. And so we have to draw the graph of the absolute value of x minus 2 and the graph of negative x on the same axis. These are the two graphs here. This is the graph of the absolute value of x minus 2, and this is the straight line y equal to negative x. And so how do we obtain the solution of this inequation from these two graphs? We are simply going to read off those values of x for which the graph of the absolute value of x minus 2 lies above the graph of negative x, lies above because of this inequality sign. If here was less than, they will be looking for those values of x for which the graph lies below. But at this level, we have greater than. So we are looking for those values of x for which the graph of the absolute value of x minus 2 lies above the graph of negative x. And these are the two graphs here. So we can see clearly that the graph of the absolute value of x minus 2 is always above the graph of y equal to negative x. There is no portion for which this graph goes below this one. We can see from here that these two lines are parallel. And there is no way this line above can ever meet this one below. The two lines are parallel, so they will never meet, regardless of this going below this one. So we can see that the graph of the absolute value of x minus 2 is always above the line y equal to negative x. And therefore, the solution set is the set of all real numbers. Good. So we are saying that the absolute value of x minus 2 plus x is always positive for all x in R, for all real values of x. Good. So those are the three methods you can use to show that the absolute value of x minus 2 plus x is always positive. Thanks for watching, and please do not forget to subscribe to this channel if you have not yet done so. And don't forget to hit the notification bells because the best is yet to come.